You're welcome. Heck yes. I'll jump in now too. So I'm done with mine. And maybe I'll quickly just load my 3D Derby car one as well because I've lost it. So maybe I didn't. Did I make an IPJ file? Yeah, I did. I made an IPJ file too. So now I've got both of them. Whichever one's checked mark is the one that I'm going to be actively looking into. So I'll set that one, say done. I'm going to go ahead and open my solid where we left off yesterday. This is it. I'm going to open my old one too, just if I need to reference it a little bit here and there. Which then if you're driving outside of where your IPJ file is, you'll get a warning like you're looking outside of that. This is the one. Yep, I'm recording. Yes, yes. So there's my original one, but here's the one I'm working on. Okay. So what one thing, so as I was just looking through this later yesterday, this is my SEMA resources here. Um, I made my flange a quarter inch thick yesterday, and then I just kind of perused through this just to find it. I would say it's a little bit ambiguous and not super clear what materials to make your flanges out of here. Um, but I did come across that my kind of my supports for this thing. I'm just going to show you here. I think they were just underneath here. Like these supports and these supporting feet, as they would call it, which we are going to build. They're recommending for our size here that they will be using. Of course, they have the dimensions for them, but the material is here, D, um, or actually it's F. Yeah, F is this material thickness. They're using 3/16 here, so I'm going to use 3/16 on my flanges that are on the housing. The end plates themselves, they're explicitly called out, I think, to be heavier. Let's take a look here. I think they're just above my housing, maybe is the end plates. Bearings, some dust seals. Here is an end plate, but I think they have some dimensionals right here. I end up using kind of both styles of this, a round one on one end and a rectangular one on the other, just because I have a discharge right to the end plate is one reason. But on here, if I go to my materials, and I think it's variable, which one? K here, maybe? K is like a thickness. I could zoom in this so you can actually see, but K is our end plate thickness, whether it's the rectangular ones or the round shaped ones. They're both K dimension. K is quarter inch plate. So I'm just going to use 3/16 plates for my flanges and supports on my housing, and I'll use quarter inch end plates. That's kind of common. Sometimes you have matching materials. Um, Sometimes if I'm a small company and I'm just trying to bundle everything as the same type of material, I might bump them all up to quarter inch material. Then I don't have to like switch materials like in a cutting process if that's what I'm doing, or have different materials on hand. So there's reasons why I probably wouldn't go down to 1/8 inch, right? I'd probably, if I was going to change materials, it might be slightly heavier rather than go lighter and risk affecting some design element with lighter materials that would be detrimental to it, like it didn't hold up as well. But always, obviously, always going heavier, you end up uh, maybe making things substantially heavier and way overbuilt. So, so as a drafter and designer, maybe I'm careful not to change materials unless there's a discussion around it. Here, I'm going to go with 3/16, but I'll use quarter inch for my end plates when I get there. So what I've got to do is, the last thing I did was extrude this thing and put the holes in it. So I'm just going to go back to this extrusion that I made that was the flange extrusion. I'm just going to do a quick change this to 3/16 plate, which is 0.1875, but you can always enter 3/16 as well. So that's going to be my flange thicknesses there. Where that'll impact is that, and it'll impact, I do a couple of supports, if you see my other file, which are just because this is a long I'll look through this manual and see if it ever mentions like adding additional supports along a housing just due to its length. Um, Mine has those added, and I can't remember if I pulled that data out of this or I just did it intuitively because of an 8 foot span of sheet metal, 12 gauge, can flex and bow. And so I'm not going to do those yet, but I have those U-shaped supports that are just they're just a structural supports to that sheet metal. Uh, yep. Yeah, because yesterday when we finished, I think I had extruded that to quarter inch, just when I it was just what I thought was they were in my head. So I went through and perused the manual. I'm like and my other model I did use 3/16 as well. And I think the reason why I did that was because of some of those parts being 3/16, and it's not explicitly called out. It could be in there. I just might have to even dive in a little deeper to see if I come across that. And so I'll put the flanges up here on the inlet side too out of 3/16. But from here, I think I think I'm gonna try to wrap up this end, which is put the end plate on it. And then the oh yeah, for my holes, because I had my sketch done. Here's my sketch for my flange, which I use points for my holes so that I could use the hole command. Oh yeah, sorry, geez, I didn't forgot to cast that way. Yeah, so th this was my original sketch here, which is mostly driven dimensions. With my holes slightly, slightly located different than they are in that manual, but more of a symmetrical flange, which I definitely look for in flanges. If there's not a reason to make them, if there's a reason to make them not symmetrical, then I stay that way. If there's not a good reason, then I definitely like symmetrical flanges. I have control over the discharge of this myself too, as I'm going to build the funnel that discharges. So I just need to make sure it matches. My flanges match. That's going to be the most important of anything, is that parts match together if they're going to bolt up to each other. But so I've made this slightly different, but symmetrical. And then I used the this whole command, and I think I just did. These are, when you use the whole command for the way I'm using it, which is just a right here as a clearance hole and no kind of seat or nothing fancy. This is just a through hole. Then I can pick what hardware it's going through, which I did. It's 3/8 hardware, a 3/8 fastener is what we'd say. And so I set all that, and then it will allow me to choose kind of those classifications of holes, whether they're close, normal, or loose. I chose a normal fit, which has got clearance around it. It ends up making a 0.397 diameter hole through the part, and I have a fastener that is 0.375 going through it. So I have clearance so the bolt won't, not a size on size relationship here. And that's how I did all my holes. And then, of course, I just had them terminate my sketches on the bottom side. So I had them terminate just the top side of the flange. And that's what I've still got. So I'm going to build out the end plate now. And the end plate, I'm just going to use this face as my end plate sketch, I think. Yeah, I mean, I could establish a plane, but I'm just going to use the plane of this solid here. And so let's sketch here. Oh yeah, you sketch on that plane. And then I'll just go to my manual here and just take a look at this end plate. I happen to be on it right there. This is page 29 out of our PDF, which is trough ends. Here's my 10-inch trough ends. Depends on what size of shaft I'm going to drive. The reason why that is because the drive shaft comes through the end plate to accept a bearing. So the end plate does a lot of work. It's going to kind of hold the form of the end of the conveyor together for one, because sheet metal's kind of flimsy if you don't like bolt it together, weld it together, whatever. And so the end plate functions as kind of it supports the housing on the end by bolting to it, and then it supports the hardware that we need for the bearing, and the shaft passes through it, and then we'll have to use a seal plate behind our bearing. Like they don't show that well here in these views, but uh, for a lot of applications, this might work just fine. Just have the bearing right to the end plate. But in other applications, we can put a seal plate, which we built a parametric seal plate last semester. We're not going to use that necessarily that model, but we're going to use a similar type of seal plate. And of course, we'll apply the O-rings and some of the sealing components to our seal plate, which usually they're just machined out to accept O-rings and some other kinds of uh, O-ring seals. So we're gonna have to worry about that, but that doesn't impact our end plate too much, other than just the hole pattern for the bearing is kind of impacted, and then knowing what size a hole needs to go through it for the drive shaft to just pass through. You wouldn't want your drive shaft to rub on this, so the hole definitely is going to be a clearance hole where that drive shaft comes through the end plate. And so, but what I'm going to look at here is just kind of get a feel for these variables and these dimensions. So what it just is. So I'm picking a 2 inch here. Obviously, with a 10 inch conveyor, I could either drive it with an 1.5 inch drive shaft or a 2 inch drive shaft. So I chose two. We've got whole potato. Maybe that's a good reason for it. A little heavier drive shaft. Um, so what's the A dimension on both of these? Whether it's the rounded one or and I'm more going to look at kind of one like this, but not necessarily this whole pattern because it's not going to be the whole pattern that's going to match how I'm going to mount this to mine because mine is a discharge that's flush to the end, and that kind of changes the end plate and how it bolts on a little bit. I think all the end plate data is here, but there is, there's this when I was looking at my trough ends down here or my feed and inlet chute page, feed and discharge chutes here. Um, the second page down here was when we have a flush end discharge like ours. So once you do that, you end up, they don't give you the whole pattern here, but they give you kind of a good representation of how I would bolt this on. And so my end plate is going to end up being a little bit more like this, where I have to build some flanges against my housing here to bolt this end plate onto. But what I'm going to do is I'm going to make the end plate first, and I'll make the flanges on the housing that it supports to. I could do it the reverse way. I don't know why. Just in my mind this morning when I jump into this, I'm like, I'll make my end plate first. But I could absolutely make those flanges on the side, which are right here. They're just vertical up right. They're making this little sandwich here. There's a flange there. You can't, it's hard to see there, but that's what that's going to be bolting through is something that's been welded to that housing, kind of like this flange has been done down here. So with that in mind, it's just a little bit of a modification on what they're showing you here where they're detailing out the dimensions. Which did I go too far? Maybe so. I memorize this thing by scrolling for the most part and remembering kind of obviously not remembering very well, which I go into my screw, then I go to the flights, then I go to a little bit of hardware and end shafts. That's all. And then I get into my bearings a little bit. And then this is the one I'm looking for. Oh yeah, page 29 is what I'm on here. So this overall width, what do they have me as? 14 and a half. Okay. I'll check that really quick, that A measurement, because what I want it to do is I want this end plate to pretty much maybe at the most come out flush from here to here, but of course on this end right here. So what is that dimension? I'm just going to measure it real quick. This from here, from outside of my flange to outside is 14 and a quarter. So this particular part is asking me to make it 14 and a half. I probably made it 14 and a quarter to match, so it didn't like go beyond this particular flange. So I might break a little bit of a rule there on this 14 and a half dimension. Only because it's going to match my flange a little bit. Otherwise, it'll be a little big. Then what do we go? Without seal, with seal. What's B? I gotta just analyze this. B. Okay, it's maybe not something I'm super concerned about, but it has to do with the seal and how the bearing fits on it. Okay, that's not the most useful information yet. Mine might not even be that, and it doesn't really matter as long as I'm supporting my shaft with my bearing. So because I might have a little bit different setup than they have going on here. So this might not be a hard hold for me at this point. C is what? The top flange. They're saying this is kind of an OD. I'll zoom in a little bit. Outside dimension from here to here overall once the flange is bent on. Maybe I'm trying to get 1 3/4 there. Again, I could probably vary that if it needed to match kind of the lids that go on mine eventually. So this might not be a really hard held, real critical dimension, right? So, and then I've got let me zoom out a little bit here. 8 7/8 is E. And so which one is E? Okay, so this is from center down to the bottom. I'm just going to make mine match. So this could be what I need, but this isn't kind of an outside dimension as well, kind of from the outside to the center of drive shaft here. They're saying 8 7/8. I'll see here. 1 3/4 F G F G. Kind of wondered if they called out the whole size through the end plate here. I'm kind of surprised they don't, but F G H. H is the size of bolt. What is H? H is a 1/2 inch bolt. Of course, that's a little bit different style because what they're going to do is almost support it to some kind of a mount with this slotted fastener where H is. Mine's going to bolt through like the flange that we started yesterday. So I'm going to probably plan on mine having 3/8 hardware along here rather than this kind of a setup on the foot because I'm using mine as part of the flange. So it's a little bit different than what's going on there. J and K. K is the material thickness of 1/4 inch. I'm definitely going to stay with that. What's J? J would be the spacing on those if I was doing that kind of a footing. 9 1/2. And then what's the 5 1/8? Wait, what's the variable? L on that one? Hmm. This is definitely L, as they're saying this is the bearing bolt pattern, but it depends on which bearing I'm using. So that one may or may not be useful. So I'll show you. Okay, so what we'll do is we'll dive in here a little bit. So I'm going to use this as kind of a reference, but I might go off script just a little bit. So, and that could be a normal part of, building a screw conveyor is like, I'm going to use this as reference. Mine's slightly different. I'm going to try not to vary too much from this, but I've got to make it work how I want it to work. And yeah, there are times when engineers and design groups will change up, use this as a reference and then say, this is actually what's going to work for us better. Something that we use over and over again is this type of a fit up, and so we like this arrangement better than maybe what's in a standard. So we could depart from that and say, well, for our company standard, we're going to do a flush discharge, and that's going to change some of the components of this. But overall, I think I'm going to match my overall size. So here we go. I'm going to come over here. I think I've got an idea of how I'm going to proceed here. What I'm going to do is I want to potentially reference the overall width of this. So I'm going to project some geometry. I'm in this sketch on the end plate. I just want to know how wide mine is. And I'm not going to exceed the width of my flanges there like that. So I'm referencing how those are. Um, yes, I think so. I think that's what I'm doing. And then I'm going to draw a rectangle in here. That's the size that I need, which is what I'm going to think of here a little bit is this is the top of my inside of my conveyor. When I bend on my sides with my sheet metal, they are going to bend like right over from here and then down and kind of like go around these flanges, kind of hook them into their. Anyway, we'll get into that. But what I'm thinking of, the top of this or the top of mine is going to be really the topmost, I think. Yeah, I think it's going to be the top. The Once I bend my flange on, I'm going to make sure I don't like bend it the wrong way and have it be larger than that and be higher than that. That's going to be the highest part once the flange is bent on actually across this top of its housing. And so what I've got here, if you look at how mine is kind of weird, it looks weird why it doesn't match here. Well, it's because I'm going to bend this part as well. If you think of our end plates have a bend on the bottom and on the top. It's almost because they're going to be like a really stiff, really secure end plate that's going to hold this housing in its shape here on the end and support a bearing and support a motor and gearbox. So this thing's going to take some some weight hanging on it here in some ways. So I'm going to bend this And I'm going to do the same way as when I bend this plate, which is going to be quarter-inch plate. I want it to finish so that the flange doesn't go taller than that overall housing height here. So I'm going to incorporate that into it. At least I'm going to guess my best guess into here. Of course, once I start bending the material with the sheet metal part, I may have to make some adjustments to my solid or something. But what my plan is to make this maybe a quarter-inch short of top. So that's because that's the material thickness. So from here, I'm measuring from here to here is a quarter-inch. That's because I'm planning for this end plate to bend, and pretty much I'm going to gain a material thickness when that bends, and then the top of my flange will finish with the top height of this housing. On all of my flanges that come off there is what I want. I want them to line up so they're all on the same plane once they've bent, even if they're made out of different materials, which takes some planning here. And the same way here on the bottom, I'm sure that I've held this off a quarter-inch probably from where our flanges were here. This is the bottom of our flange to here. It's a quarter-inch because I'm also planning for the material to bend around and come out. And so that's kind of how I'm going to go. I'm going to make this thing so it matches my overall width like I did here. From there to there, it's going to be the width of my end plate. And then the overall heights are going to be just short by a quarter-inch so I can allow for a bend. And then I've got to come up with some hole patterns in there and hole sizes. Okay, so what am I thinking? A lot of this to me is like if I think of the end plate design, really the biggest the most critical part of this is definitely the hole through the center where the shaft comes through. Like it has to be in the right place. Otherwise my Otherwise, this is where I'm supporting the shaft and the auger, the screw through this. If I don't locate this correctly, it's going to be too low in my housing and rub on my housing, or be too high and hit my lids or something, right? Like I have to make sure that that is dead, that center hole. So to me, I might drive this part at least considering that location. So let me go over here and at least like think of that when I'm in my own space here on my new part here. That, and I'm in my sketch here. This is that point. The way I've systematically built mine with my origin planes, this is going to be center. So, so that's really critical. That's where that hole ends up in my end plate. So I have that. That's good. I think I can select that when I go to put that circle in there when I determine how big that is. But I'm just going to keep my eye on that. That's super critical. And then I can do the rest just like let's see here. How might I want to do this? Well, from here, I might project this geometry as well, this piece here. And I might project the topmost to keep track of it here. So I've got these things projected. I generally turn those into construction material if I can.
Did you project the like waist strokes off bottom?
Yeah, I projected this teeny little piece out here just so I can get the overall width from that one to this one over here. I just kind of projected that little side edge. And then I've projected this one and this one. And this one is because what I'm keeping track of is from there, I need to go down a quarter-inch to where my end plate actually starts. From here, I need to go up a quarter-inch. So I could offset that line to have something to lock into, or I could dimension. I can also do something like, oh, I don't know how I want to start this, but just start it. Just do it. Yeah, but I need to know like a quarter-inch up from there. So I could offset these, and I've probably drawn it different on the example that I posted. But yeah, I'm offsetting this like a quarter-inch, which is really just reference material as well, right? This is just reference material. From there to there, maybe I'll offset this one the same way. And you don't have to build this. If you see geometry different, if you can kind of see where we're trying to get, you don't have to exactly do this how I do. This is where we definitely can take different routes down a ski run and get to the same place. So, but this kind of helps me bind in my overall dimensions of my end plate. So I'm going to have this rectangle. If I pull up a rectangle command, it's going to end up being, out here somewhere. And then it's going to come out here to about there. I just don't want to snap into anything yet. I'm kind of, sometimes when I'm just like getting a feel for how this is going to work, I just won't, I don't like to snap into a point that I have to remove the constraints for. So I just kind of avoid it. And then I can massage this into being how I want it to be. So I've got my rectangle. I'm kind of locked in on the top because I did project, I kind of cursored over from that and it did lock me into that top. So that's definitely the height of the top of the end plate. Then I can just use some constraints, like some geometric constraints, which I use my horizontal and vertical constraints a lot here. If I choose my vertical constraint, I can say, well, I want this side to end up. Let me cancel that, make sure I'm not doubling up a command here. I want this side here to line up with, it doesn't want me to allow me to do that. I can pick my endpoint maybe. So there, I'm really not, I can still stretch this down. I'm going to lock that in to this line here. But what I've done is I've locked it in, vertically constrain it to where that projection was for the overall width here. I'm going to do the same thing on this side. So I'm just choosing my endpoint here actually of that. And then I'm choosing an endpoint here or my line or something. I should be able to choose my line. I think I've got to choose a point. There we go. So I'm constrained around three sides now where my endpoints will live. And then I just got to do the bottom one, which is going to be a horizontal constraint is what I'll use. I'm just going to horizontally constrain that to maybe the endpoint of this line here. So really it didn't take any dimensions to place that except for just the offsets here. And in fact, I could even change this one. This is what I also like to do when I've got the same dimension. I'm going to drive this by this dimension. And then I just got a one single data input here and then a bunch of just geometric constraints to hold it there. So this will become my end plate solid. Of course, now I'm in my sketch and I can kind of visualize that. So now I can probably put in my hole pattern the same way we did with some points and put in the center hole and even the hole pattern for the bearings. I can do all that here in the same sketch. I've just got to know what those are. So I know that the hardware to bolt it together, I think is 3/8 hardware. I don't want to be confused by what they're saying to bolt it together on the bottom. That's 1/2 inch hardware. I want to see, do they ever call out any of the hole size around? It's kind of funny where they help you and then they also just leave you hanging a little bit. I'm pretty sure I just use the same. And the reason why to bolt it to, I'm going to use the same hardware. And this is another kind of systematic approach. I'm using 3/8 hardware to bolt this together. It would be helpful if this end plate bolted on with 3/8 hardware as well. It's like, the same tool to disassemble rather than having to switch out tools for different hardware, which you have to do. There's reasons. I mean, you can't keep everything the same hardware everywhere, but here would be nice. There's no reason why I couldn't. They don't explicitly call it out in this what to use here. I don't think I see a single reference to the hole through the end plates here. So I'm gonna go 3/8. I'm gonna go kind of with that end view down here. I'm gonna leave that page for a minute. I'm going to use this one. I have this view in mind a little bit. I think I'm going to look at what a four hole pattern would look like here, and just decide what that spacing is. If it seems like it's overly large, then I can narrow that up. Or if it feels like it's overly small, then I can subtract one of these. I think I ended up using a four hole pattern though. In mine, it worked pretty well. So let me go out here, and we can probably come up with something. Yeah, they don't give you too much information on what that spacing is. Pretty close to the flange, but it's got to be far enough away that my hardware doesn't like once I bend that on there that it doesn't the head of the bolt has to be able to fit there. So I definitely want to come away from that flange a little bit. I can pull up my other drawing and see what I ended up using because I'm sure I just chose something that looked like it was going to work because it's not, I don't see that I have it explicitly given. Some of these are given in other, I thought maybe there was some. What else has a whole pattern like that? And maybe I'm just perusing through it too fast here, but I think there is a sheet that shows some circular hole patterning like there that gives me the size, which is helpful because this one is kind of in where I'm working from one end to the other. So their M size bolt is what? 3/8 here. Yes. So I'm on the right track. I'm bolting into something similar to that, like where my end plate would bolt into. So 3/8 I'm happy with. But they may never give you an explicit. I don't think there's anything else further down. These are just reference sheets. I think there's some they have some sheet metal dimensions in here I noticed the other day. So the very bottom has some pretty good reference information for general materials. But I was thinking, just let me look one more time, peruse through here. I don't think there's anything above the screw itself that was helpful towards that. Mm. In any rate, I'm not going to worry about it. I'm going to put in a 4-hole pattern. So how I'm going to do mine is I'm going to reference what I did here. We came in 5/8 from here to here. So I'm going to use that same dimension as how far I'm going to come in on my end plate, 5/8 here. So I'm going to have this little this point. This whole pattern will be good. This is one that I can do rows and columns for. Um, so I can establish my points along this side and then just I could mirror them over, yes, or I could do a rectangular pattern potentially here. So let's do that. So what I'm going to say is I need a point for the first bolt somewhere in here, right? So I just place my point. One dimension that I know I want is 5/8 over from here to here, which is 0.625. Technically, I could go reference that in my f of x and have that driven, and that might be smart, and that might be something I come back to later when when I'm really massaging my model to minimize data inputs. I might come through and change this to be driven by wherever I was the first 3/8 bolt hole that I put down. So, or the first dimension for that in that first flange we did. Right now, I'll just go ahead and use it as I kind of think of it as an individual sketch, even though I'm going to try to maximize my data in this sketch with, or minimize my data in this sketch. Eventually, I might be able to come back and even rework this more later in a different phase of my design process. And if I have time. Otherwise, it's 0.625. And then we came kind of when it was the first one in the series along a side, we came in also 0.625 of an inch there. So if I take a look at what that might look like, it would be from here to here with my first hole being this same dimension. And this is probably a pretty safe bet for where to begin my whole pattern for bolting these together. Because what I'm going to also have to do is build the mating flange against the housing that's going to accept this end plate. So that's good. And then you can use, like, I think a little bit systematically here, like eventually, probably down here, I'm going to end up being like the same dimensioning for another point right here. And then I want to break that up with two others. So I'd end up having like 1, 2, 3 spaces between those. So you can do some calculating, calculate some math to know how far these would be to set up a rectangular pattern. Sometimes I think that way. And what I mean is I would say, oh, so you're going to have like this bolt hole and 1, 2, 3 others. I want them equally spaced, and I kind of want to end up down here at like 5/8 by 5/8 so that it's in this location, but off this corner. So we can just calculate what that would be, right? I have a measurement tool here, like from here to here. Sorry, here to where my end plate ends is what? 13 3/4. So this is how I kind of work in some ways. Like 13.75 is what my overall kind of end plate is here. I'm going to subtract 0.625 because I come in from the end 0.625. Then I subtract coming in from the other end 0.625. And I end up with like 12.5 inches from this hole to the other hole on the other end. And then in between there, how many spaces do I have to put in 2 more holes? Well, I have that 1, 2, 3 spaces. So if I divide this by 3, it ends up with a 4.1666 kind of repeated. So that's going to be my spacing in between. So this would be a number that I could use for a rectangular pattern to put these in. So I'm going to keep this in mind. It's a 4.166 is going to be my hole spacing. 4.1666. I'll probably go out to 4 decimal places there. And I just need to figure out how far over that column would be if I'm going to do this as a pattern. So the column is going to end up being over here. So the distance it's going to be apart is if I say, okay, and I measure from my end plate here, which I think is 14 1/4. And then I'm going to come in 5/8 off each side of that, right? Each side of that. 14 1/4 minus 0.625 minus 0.625. It's going to be 13 inches between those. So, okay, I feel like I have my numbers to do a pattern here, is what I've just figured out. And so my pattern will be a rectangular pattern of this particular hole or this point. That's all I'm going to really pattern is a point for holes. My first direction can be my columns. Sure. So I'll choose my geometry on my plate here. I want my columns to be that way, and I want them to be, I only need two of them, this side and that side, but they need to be 13 inches apart like that. So there's going to be the other hole over there. And then for my direction, for my rows, I'll just pick this geometry as well outside, and I'm going to flip that so my rows go down from here. And they actually need you include the one that I've got highlighted, so that's why there's two showing there, right? I end up with needing four holes crossed here, and I need them to be that kind of odd number that I figured out, that 4.1666 apart. And this is going to end up putting a pattern in. So patterning works good for this. I had a little issue trying to use a pattern for this because there's the rows and columns aren't totally complete, right? However, what I want to just say is like you can do what I'm doing here, and I could have ended up with holes like here and here if I did a row and column pattern over here. And then you can suppress those if you want to. That's definitely a way some modelers will do that. Go ahead and do the full row, do the full pattern, and then just suppress the ones I don't need. So in this case, this is a good candidate for not needing to suppress any. It's clean rectangular pattern. So I just say, okay, and those things are ready to make holes out of with some minimum data inputs. Yes, I like it. Okay. And then we need a hole for my bearing. So that one I just haven't come across that on my sheet yet. It's a 2-inch shaft. I know that. And I was thinking that it was in this sheet somewhere. So if you've seen it, let me know if you've come across somewhere they're going to call out potentially a hole size for that. Yeah, I'm anticipating it being like 2 1/8 or something around there, like a 16th inch at least of clearance all the way around. It could be bigger than that. I just don't want my shaft to rub on my end plate. That's a pretty common problem when bearings fail. And so if you have a little more clearance, it helps not destroy your shaft if bearings fail. So let's see. Yeah. End plate, trough ends with feet. It could just be on something that I'm not. There's C, end plate, B is overall length, D. Just giving me some bearing issues here. Let's see here. Sorry, there is a lot of research to kind of go to proceed. I know, I understand. That's pretty normal. Um, Not an explicit size. G was nothing that was, what was G? Uh, oh, G's the bottom foot flange, are telling me. Okay, yeah, just not clearly called out in the whole. Let me see what I did, and I'll wonder where I got my information. I probably just need a little. I probably just need to do a little more research. But what did I measure mine at? And I might find it. So mine is 2 1/8. So I'll put that in to match this one that I've done, and I'll see if I can find where I pulled that information, and if that's enough. So we can always come back to the sketch, repair that later on it'll repair our part if we've built it from this model. So I'm going to go ahead and throw it in at least 2 1/8. I know I need it to be clearance. Whether that's enough, my next question is that enough clearance? Because it's a 2-inch shaft coming through. That's not a lot of clearance for this particular application, but so I'm just going to choose that endpoint where that lives, my center point, I should say. You can project it if you can't grip to it, but this is going to be a 2 1/8 inch hole through this end plate like that. And then I can put in the bearing, mounting. And so what? Oh yeah, 2 1/8. And it's snapped to essentially my center point of my model is that is that point where I'm constrained to. So that's why mine is constrained, because I snapped it to that center point, and that is center of shaft. Now we just need to know the bearing. Like I would like to have the holes for the bearing here, and I'd like to do those probably with a point as well and use the hole command. And let me just speak to that a little bit, looking at this. When you bolt on bearings, you have some options, but and they're telling us, I don't know if they give us the hardware for that necessarily. So I think I'm going to let the bearing drive the whole pattern plus the hardware that to bolt it up based off of what the bearing looks like. So we're going to go to McMaster Car here, and we're just going to get a feel for what bearing I'm going to use. But what I want to say is the way they mount these to end plates is, yes, you could just think of it as a bolt going through. Um, and that would put, like, in this situation, if I'm looking at maybe how that bearing is bolted on there, maybe they would have the nut on the inside, or sorry, the head of the bolt on the inside of the trough, and then they poke it through and put a nut on it after it's bolted through the bearing. So it has to be, the right length of fastener to hold all that together. But that puts the head of a bolt on the inside of your auger, which is, in some cases you have clearance. We don't generally bring the auger flights, the screw flights, like clear up to the end plate, but sometimes in some situations we bring them very, very close because, especially on an inlet end where I'm dumping product into a screw conveyor, I actually don't want to have a bunch of product packing against the end plate and have this big voided space where the flights start to push stuff through versus just kind of hang out there and don't get pushed through. So they, on the inlet sides of screw conveyors, they'll bring those flights like, dangerously close to the end plate in some cases, just so that I'm wiping as much as I can and not packing behind my where I'm feeding it in. And we'll kind of see what that looks like once we get an auger in here and see how it spins in there. And there's going to be, I think they do this manual does have some good minimum spacings off your end plate type data, because that's critical stuff for sure. But having a bolt head on the inside in that area, especially on the infeed end of a screw conveyor, can be, some bolt heads can be kind of large and they can end up, and I don't want to rub my flights on a bolt head either and shear them off or whatever. So you will see like a real standard when I have something going on like this, where I've got to really preserve the inside of something and keep it as smooth and clean as possible, and keep any kind of hardware that might be interfering with my screw just away from it. What they will do is just use a piece of all thread for a fastener. So they actually will use a headless piece of all thread, is just like threaded rod that looks like you could make a million bolts out of it. It's just a long, it doesn't have any heads on it. It's just a threaded rod is all it is. And they will cut it to size, and then they will tap or thread the end plate. And then they will just like screw in that all thread, and then to hold that in there, the welders will actually go to the inside of the end plate and they'll do like a plug weld. This is a good application for a plug weld. They'll plug weld the all thread into the hole on the back side. And so it actually can't be removed without drilling it out or breaking it out. And but it can be removed. That's one thing. But yeah, and then you don't have a head of a bolt on the inside of your housing. You just have all thread with a weld against the inside of the housing that can be ground smooth, because you can like thread the all thread in a little ways, like halfway through the plate, and then do the plug weld it in there. So you've got some threads acting for mostly for alignment, and the weld is really going to hold that fastener, which is a piece of all thread, in place. So that's kind of how I'm going to proceed with this. So I don't have a bolt head on the inside. Why I tell you that is because it kind of impacts this part when I make it, that I just make it so it's threaded. Okay, so with that in mind, what I need to know is the whole pattern for the bearing. And so on my, I'm going to open up one more reference sheet, which is the design specification from engineering sheet that I have. Mine's just, I can open up mine for my file here. Maybe bear with me. If I finish this end plate, we'll just take a break there and do the flanges for it. I'm getting close to being done with my end here, I promise. Let's see here. It's the screw conveyor guidelines. This one, my design. It's the Word document of a resource. This one here. What I did is I just kind of, and this is pretty common from engineering or from working in a company. They might already have picked out bearings that they're going to use. So there's really no, as long as you find the right size of bearings. So what I have to know is if this side is my driven or my drive end. And so the discharge on our conveyor is going to be the drive end. So what I need to know is the drive end bearing. And we'll talk about that and why maybe I chose that way. But I could drive from either end. You can either think of it as putting the gearbox and motor on the infeed end and push and use use the gearbox and motor to kind of be on the drive end would be on the inlet end, and we would be pushing all the product through. In this case, I'm putting the drive on the discharge end, so I kind of feel like I'm like pulling the product through, pulling it through. And usually I think there's good and better and best designs, but you'll see augers bolt done different ways. And I feel like sometimes that falls on engineering to decide which is the best way to drive this particular. And sometimes what drives it more than anything is just where I have room to put the gearbox and motor, because technically I can usually drive a conveyor from either end, but sometimes I'm more limited to space on one end than the other. And so I'm definitely I want to put it where I have room. Gearboxes and motors need maintenance, regular maintenance, and sometimes they have to be changed. And so you definitely don't want to bury that thing in underneath decking or whatever. You want to have a kind of an overall end in mind of where's your best access for a gearbox and motor to be maintained, because I can either push or pull that product through it. So in my case, the reason why I'm choosing that is because eventually I want to build out enough that I have like an access. This is going to be 8 foot or 10 foot up in the air. I'm going to need some stairs to get up to it to where I can actually access this screw conveyor. So I'm going to have stairs up to it and a structural steel platform to walk on here. And then on my infeed end, I'm going to have kind of a big chute up here, and I'm going to have another set of stairs that come up so that I can access the equipment and the where the equipment dumps into my auger. So I have in mind just eventually that I'm going to build this out as stairs up, platform over, a little bit of a landing, and then stairs up to another landing so that I can monitor my infeed chute and my even flow bin. And so if I put the driving gearbox here, it's going to kind of be in the way where I'm going to put an access platform actually. And so out here in this space is where my drive and my gearbox and motor are going to live. And I'm going to have better access here to change them out and to maintain them. So that there was some engineering thought in mind, and it's maybe understanding the overall design process, how it fits in a plant or fits in a factory, and where I can get to it. So, okay, with that in mind, this is going to be my drive end. So when I go back to this chart, I have these bearings called out, McMaster car bearings. The drive is also going to take the thrust, and so it's a special kind of bearing to accept the thrust, which just means it's got forces acting against it to hold the screw so it doesn't slide back and forth. The bearings can actually take those kinds of thrusts and lock down to try to hold that shaft from being able to slide one way or the other in the bearings. So this is the drive taking the thrust. The driven bearing is kind of just a way more simple bearing. It's just a bearing, and it even looks quite a bit different. So what I need to pull up though is this drive bearing. So I have this link on this document. And if you don't have the document open, I'll you can go to McMaster Car, because what I'm going to on my browser, because if I just hit Control and click here, it should take me to McMaster Car right here. It's going to take you right to the bearing that I'm going to select actually. So it's just a link right to the bearing in McMaster Car. If you're just going to McMaster Car, you're going to have to know some numbers to type in. Oh, McMaster Care. Well, it knows that I mean McMaster Car. And then we'd have to search out. And what I would have you search for is this particular number, this 1498N14. That's like its McMaster car part number. So if you're just going to the main website, it's going to be a 1498N14 bearing. And it should drive you down to this same one, which which is a 2 inch. It's for a 2 inch diameter shaft. And so this is the bearing. So I can actually I'm gonna go ahead and pull this model right now. Because then I can analyze the model in Inventor and just make sure that the model they're going to give me is going to match my end plate. And so this is the best way for me to like verify that I'm going to make my end plate accept this bearing. And so all I do is once I'm here, I do two things. I always pull the product detail sheets into my folder because I have a resources folder in my. So I'm going to pull these detail sheets out that are handy, and I would keep this with. And so here's my download button for that. And all I want to do is download this or save it. Not print it. I want to save it. And then just find if you did like I did and I built my file system so that I can go to my screw conveyor for 2026 for me. And I just have that resources folder so I can dump this in here. I'm probably not going to change much of it. I'll just leave it with the default. It's got its part number in it, and it's a mounted roller bearing with 4-bolt flange. Okay, so it's identifiable from just reading it from a list to me. I'm just going to save it in my resources folder. It's just going to be what an Adobe a PDF. So I'll save that. Killer. While I'm in here, always save your spec sheets. It shows. I mean, this is all I pretty much need to probably proceed here. But I think I'll pull the model while I'm in here too. And so I'll go through and open this up, the one that I saved, just to check it. I can almost check their model to their own spec sheet, and just make sure I'm not going to get something different. But I'm going to go back to this, and then I'm just going to pull the step file for this bearing. I'm going to pull the 3D step file. There isn't a inventor files yet. If you're in SolidWorks, you definitely have one ready to go right to SolidWorks. Step files are these like universally shared type of file structure, doc or file type. So I can import this easily into Inventor. They just don't have a 3D right to Inventor model available. Our Inventor models will also they can export as step files. So that's the best way to probably share something with someone else, is to just turn it into a step file. There's a simplification process when you do that is helpful for holding on to proprietary information. When you create a step file, you can really dumb it down so it's kind of as least detailed as you need in case you don't want to share sensitive information actually. So step files are super modifiable in what they look like. And generally I make a simplified model and then I send that as a step file, especially as long as my step files contains what somebody else will need to match up to mine. Um, okay, I'm going to download that. It's downloaded. I just maybe need to, it didn't ask me where to download it. So I just need to make sure I push my downloads that ended up in my downloads folder. I'm going to drag and drop that into my screw conveyor. This is good. I'm going to drag and drop it into my parts folder. It's a step file part, so I'm gonna have to let Inventor convert it, but I'm gonna pull the whole step file into my parts folder as well. I could put it into, you could have a buyout, like one more file structure I could have created was maybe like a buyouts folder where all of my stuff it's going to be purchased items. I could drop those into a different folder. I'm just going to keep mine in my parts. I think we won't have a huge, I mean, but just think about it. If you have a lot of buyouts on a particular model, maybe you want to make a buyouts folder where you just kind of compartmentalize everything that's going to be purchased from purchasing, outsource essentially, and an easy place to find those parts. But I just dumped it into my normal parts one here. And so now I'm going to go to Inventor and I'm going to open that part. So I'm just going to say open. I'm in my screw conveyor. Actually, I'm one down here. Here's my other one. Yeah, that's actually it. So in my parts, I should have this step file show up. If it doesn't show up, it's because you're just looking for Inventor parts down here. So I just need to change my file search. I just usually select all files first. And there is there's my step file. So I'm going to select that and have Inventor do the conversion for me right now. It'll give you this prompt where you can change a bunch of stuff. I'm just going to do default and say okay here. And there's the bearing from McMaster car that's going to go. And I'll be able to apply this once I have a housing assembly and stuff, I'll just be able to drop this file in. I'm just going to do a quick save as here and save it as into my part file naming structure here, just so it shows up. But I don't want to lose its McMaster car kind of in its description and stuff. So right now it's just named it it's just this big glob of a name, right? And but it has its part number in it, which I like. I just want to make sure I don't lose that before I make sure it's in the description of this part in its iProperties. So to me, I just kind of make sure that I'm keeping this documentation. It is in there already. So I'm not going to, well, this could be the title that changes when I change the title, but oh, I just chose all files. So, and the only reason why I choose that is because it's the one right above where I click on that. So, yeah, in order to see the step file, I search for all files. and it will show up there if it's in your folder. You get good at that in mechanical because we beg, borrow, and steal from other people all the time. You do it in Revit too. You're gonna be pulling people's families in all the time. Uh, a large part of modern day design is just you are the assembler of other people's already finished models in some ways, which gives you a more accurate. If I were to model this, I would probably dumb it down and I'd probably go as simple as I could to represent the bearing. And then you don't have like the most accurate digital twin, but if you're pulling in other people's models, you get a more accurate digital twin once you're complete with yours. So what am I doing here? I want to rename this as my file naming system. Um, but I also want to just double check its I properties to make sure I'm not going to lose something. Um, really, what I don't want it to be step AP20 here. I probably want it to be my description. I would just want it to say this part number for sure. This 1498N14 is a real critical number. And so I'm gonna paste that here, but I'm probably just gonna say something like oh, the description is drive bearing. I think bearing is like BRG. Does that sound right? Drive bearing. Uh, and I'm going to say something about like McMaster car. And then I'm going to paste that number in. And I'm going to delete the step file stuff. So this is, you remember descriptions show up in my parts list. This is just, so I'm going to see this show up as drive bearing McMaster. So I know I'll be able to identify this pretty easily off my parts list on my drawing. I just want to make sure I capture that. So I'm going to apply that, close it. I'm going to do a file save as though. This isn't in my numbering sequence that I want all my parts to have. So I'm just going to do my ISU numbering sequence here. So this allows me to change the file name, right? I'm going to change it to what I've got as an ISU. Here's kind of the one that I used before. It's for my solid, but I'm going to use the same numbering sequence, only I'm going to say this is part number 2. ISU MRSC002. It's only the second part I've created in this whole assembly, actually. So, and it's technically, I could see me like having a little like dash B for a buyout or dash P for purchasing part. I don't know. That could be helpful in a numbering sequence if I kind of, when I went in my parts and I thought, oh, which ones are my buyout parts? I could add something. I'm not. I'm just going to do it here and we'll see if I lose it. But when I'm opening parts in Inventor, I always have that little preview window that I can kind of click through my parts and decide, oh, that one's my bearing. But there could be a better approach to that, to identify quicker. Because the parts in an assembly like this, eventually I'm going to have quite a few parts, housing parts, discharge parts, inlet parts, even flow parts. Um, so eventually I might have a lot of parts in this folder that are going to be hard to maybe identify. So especially when they're just to a coded number system, which is common with parts. Okay, so I'll say save. And now this should be what that part number is. And now I can evaluate it for what the heck do I need to bolt this up with. So I think the spec sheet's the best one to probably reference for that. I could come in here and measure this, these holes and this whole pattern. It's a 1/2 inch diameter. So it's probably not a 1/2 inch bolt that holds that up, but 3/8 seems a little bit small to me. Um, Let me see what the spec sheet says for that, which is what I have in my folder here somewhere in my resources when I downloaded it right there. And so I'll take a break now. I'll call this part 1. I do want to jump in. I think I'm going to probably continue with this all day just to try to get the end discharge done, the end plate and the little flanges that I need to mount it. And that'll be a good place on this to end. I probably won't be starting to make parts till Thursday on this. And so I might dedicate most, I don't know. Yeah. But yeah, let's take a break. I'll call this part 1. They do tell me it's a 1/2 inch hole. They've got it's a 4 3/8 kind of hole pattern for it. And it doesn't tell me what kind of hardware to use necessarily. So I'm tempted to use 1/2 inch. I'm just worried about this being a little bit tight on a 1/2 inch bolt, size on size, right? Maybe I could use 7/16 hardware. That's just kind of an oddball hardware, but it's probably a better selection than 3/8 actually. So I'll just push, yeah, let me stop here, take a break. And we'll jump in after a minute here.